If you walked into a corporate data center in 2005, you were walking into a crime scene of economic inefficiency. It was a freezing cold room, deafeningly loud with the hum of 10,000 cooling fans, where companies were burning billions of dollars on hardware that was doing absolutely nothing. We are talking about server utilization rates of 10 to 15%. That means for every dollar a Fortune 500 company spent on electricity, real estate, cooling, and high-end Intel Xeon processors, 85 cents was effectively thrown into a furnace. The reason for this colossal waste wasn't stupidity, it was fear. Specifically, the fear of dependency. Hell, in those days, a sysadmin wouldn't dare run to different critical applications on the same physical server. If the payroll app needed Java 1.4 and the inventory app needed Java 1.6, you couldn't just install both and hope for the best. They would fight over environment variables, they would conflict over file paths, and eventually one would crash the other. So, the industry standard was isolation by access. One application, one physical server. If you needed a mail server, you bought a physical box from Dell or HP. If you needed a database, you bought another box. It was a logistical nightmare that made scaling software nearly impossible for anyone who was on Google or Amazon. You had to provision hardware for your peak Black Friday, which meant for the other 364 days of the year. That expensive hardware just sat there, consuming power, waiting for a load that rarely came. Then came the first attempt to fix this economic bleeding. The virtual machine. VMware made a fortune telling companies they could run multiple computers inside one physical computer using a piece of software called a hypervisor. And it worked, technically. It allowed the banking and healthcare sectors to consolidate their racks. But it was heavy. A virtual machine is like buying a massive house just because you want to use the toaster. To run a simple 10-megabyte Python script or a small Node.js background worker, you had to boot up an entire guest operating system. A full copy of Windows Server or Linux, which took up gigabytes of RAM and storage just to exist. You were paying a guest OS tax on every single application you deployed. The CPU spent cycles managing the virtual hardware instead of running your business logic. The industry accepted this inefficiency because there was no alternative, until a small, failing platform-as-service startup called decided to open source an internal tool they had built to save their own sanity. They called it Docker, and almost overnight, they didn't just change how we write code. They changed the unit economics of the entire internet. Before we unpack how Docker saved the industry billions in hardware costs and why it's the absolute standard for modern DevOps, if you appreciate deep dives into the technology that actually runs the world, go ahead and hit the like button. It helps the algorithm push this content to other engineers, investors, and serious professionals who care about how the machine really works. To understand why Docker was such a revolution, you have to understand the visceral pain of the works on my machine era. For decades, there was a wall of confusion and hostility between developers and operations. A developer would write code on a shiny new MacBook Pro. They would install specific libraries, tweak the environment variables, set up the perfect local database, and get everything running perfectly. Then, they would zip up the code and send it to the sysadmin to deploy on a Red Hat Linux server in the basement. And immediately, it would crash. Why? Because the server had a slightly different version of Python, or the OpenSSL library was outdated, or the file permissions were different, or the wind was blowing the wrong direction. This friction slowed down deployment cycles from hours to months. Companies had deployment days where everyone stayed late, ordering pizza, praying the site wouldn't go down. Docker solved this by stealing an idea from the logistics industry. Before 1956, loading a ship was a disaster. You had barrels of whiskey, sacks of flour, and boxers of furniture, all different shapes and sizes. It was slow, dangerous, and expensive. Then, Malcolm McLean invented the intermodal shipping container, a standard metal box. The crane operator didn't need to know what was inside the boxcars, bananas, or electronics. They just needed to know how to lift the box. Docker did this for software. Docker introduced the concept of the standard container. Unlike a virtual machine, a A container doesn't need its own operating system. It shares the kernel of the host machine, but keeps the application in a sealed, isolated environment. It's not a house, it's an apartment. You share the plumbing and the foundation, the Linux kernel, but you have your own walls and your own front door. This removed the guest OS tax. Suddenly, a server that could only struggle to run 5 virtual machines could easily run 100 Docker containers. The boot time went from minutes to milliseconds. For a company like Uber, Netflix, or Spotify, this wasn't just a technical upgrade. It was a financial miracle. It meant they could serve 10 times the traffic without buying a single new server. This is the bin packing efficiency. Docker allowed companies to squeeze every ounce of computing power out of their hardware, raising utilization rates from that pathetic 10% to 60 or 80%. In the world of AWS and Azure bills, where you pay by the minute for compute capacity, that efficiency translates to billions of dollars saved annually across the Fortune 500. But we need to be technically accurate here. Docker didn't actually invent container technology. The underlying tech, known as Linux namespace for isolation and groups for resource limiting, had been inside the Linux kernel for years. Google had been using it internally for a decade with a system called Borg. What Docker did was create a user interface for it. They made it accessible to the average developer. They gave us the Docker file. This simple text file became the single source of truth. It documented exactly what OS, what libraries, and what commands were needed to run the app. It used a layered file system, meaning if you changed one line of code, you didn't have to re-download the whole operating system, just the top layer. You could hand that Docker file to anyone, anywhere, and it would build the exact same environment, bit for bit. The works on my machine excuse was dead. If it runs in a container on your laptop, it runs in a container on the server. This reliability allowed the massive architectural shift from monoliths to In the old days, software was a monolith, one giant block of code. Imagine a bank's software. Login, account balance, transfers, and credit card applications were all one giant executable file. If you wanted to update the font size on the credit card page, you had to recompile and redeploy the entire banking application. It was risky. If the credit card code had a bug, it could crash the login page. With Docker, companies could break the application into tiny, independent pieces. The login is one container. The transfer is another. The balance check is a third. This is microservices architecture. If the credit card container crashes, the login keeps working. You can update them independently. You can write the login in Java and the transfer service in Go and Docker. Doesn't care. But the real magic is scaling. If everyone is logging in on payday, you don't need to duplicate the whole banking site. You just spin up 5,000 more login containers in seconds to handle the load and then shut them down when the traffic drops. This elasticity is the only reason modern hyperscale applications exist. You cannot build TikTok or Uber using the old virtual machine model. It would be too slow and too expensive. However, Docker's massive success created a power vacuum. Docker, the company, had the runtime, the engine that runs the container, but they didn't have the orchestration. Running one container is easy. Running 10,000 containers across 500 servers, making sure they can talk to each other, restart if they crash, and scale up and down automatically. That is a nightmare. Docker tried to solve this with a tool called Docker Swarm. It was simple, easy to use, and integrated perfectly. But Google, watching from the sidelines, decided to release their own internal tool as open source. They called it Kubernetes. The container wars of 2016 were brutal, but Kubernetes won. It became the operating system of the cloud. Kubernetes is complex, difficult, and verbose, but it is powerful. It allows you to declare the state of your system in a text file. I want 50 copies of the login service running at all times, and Kubernetes ensures that state exists. If a server catches fire, Kubernetes notices the 50 copies drop to 40, and it automatically starts 10 new ones on a different server. Today, Docker is still the standard format for building containers, but Kubernetes is the standard for running them. This actually hurt Docker Inc.'s business model, proving that in open source, you can change the world and still struggle to monetize it. We also have to talk about the philosophy shift, cattle versus pets. In the old days, servers were pets. You gave them names like Zeus or Apollo. If Zeus got sick, crashed, you paged a sysadmin at 3 a.m. to nurse it back to health. You cared about that server. In the Docker era, servers and containers are cattle. You don't name them. You give them numbers. If Container 459 gets sick, you don't fix it, you shoot it. You kill it and spin up container number 462, replace it. This is the concept of immutable infrastructure. You never patch a running container. You build a new image and replace the old one. This eliminates configuration drift, where servers slowly become different from each other over time because of manual updates. This makes the infrastructure incredibly resilient, but it also requires a completely different mindset from the engineers running it. Of course, we must address security. In the beginning, skeptics, mostly banks and government agencies, said containers were insecure because they shared the OS kernel. If a hacker broke out of a container, they owned the whole machine, and they were right to be worried. But the tech has matured. Today, we have distroless images containers that contain only your application and absolutely nothing else. No shell, no package manager, no tools for a hacker to use if they break in. The attack surface has shrunk. However, the complexity has skyrocketed. The modern cloud-native landscape is a dizzying array of tools: Prometheus for monitoring, Istio for service mesh, Argo CD for deployment. We traded the problem of dependency hell for the problem of architectural complexity. We saved money on hardware, but we are spending it on salaries for DevOps engineers who understand this insanity. A junior developer used to just upload files via FTP. Now they need to understand CI/CD pipelines, container registries, and YAML indentation. The irony is that Docker became so successful, it became invisible. Today, you don't really think about Docker. You just expect it to be there. It has become a utility, like electricity or running water. But for the aspiring developer, system administrator, or tech investor, this is the baseline. You cannot get a job in high-level tech today without understanding containerization. It is the language of the cloud. The days of manually configuring a server are gone. The pipeline is now automated, containerized, and orchestrated, and this has economic consequences for your career. This brings us to the financial reality of the job market. The engineers who are just writing code, the function writers, are becoming commodities. The AI can write code. GitHub Copilot can write functions. ChatGPT can debug syntax. But the AI cannot yet architect a resilient, scalable, containerized infrastructure that saves a company 40% on their cloud bill while maintaining 99.99% uptime. That is where the leverage is. The value has shifted from writing the app to delivering the app. If you want to survive the next decade of tech, you need to understand the plumbing. You need to understand Linux internals, networking, how these containers actually talk to each other, and how to secure the supply chain. If you are tired of just being a coder who is easily replaceable and want to become an architect who controls the infrastructure, you need a structured path. You can't just learn this by guessing. I've put together the Hacker's Blueprint, an SA3-in-1 bundle designed to give you the hard skills that companies actually pay a premium for. It includes the Python Masterclass for automation because you need to script the glue that holds these containers together, the ethical hacking manual to understand how to secure these containers against breakouts and supply chain attacks, and the cybersecurity protocol to understand the network layers that Docker relies on. Docker and Kubernetes are powerful, but they are dangerous if configured by amateurs. A misconfigured container can expose an entire database to the public internet in seconds. This bundle isn't about learning syntax. It's about learning systems. It's about understanding the machine so well that you can make it do whatever you want. Stop letting the tools control you. Check the link in the description, grab the bundle, and start building your leverage today.